In this video, we're going to discuss rolling motion as well as angular momentum and conservation of angular momentum. Rolling is a combination of translation of the center of mass and rotation of the rest of the body around the center of mass. We will assume that there is no slipping. So if you look at this first diagram, you can see a wheel that it's rolling, and it's rolling to the right. You can see that its center of mass is at 0, and it has a velocity of the center of mass, and where it touches the surface is point P, and point P, as the wheel rolls, moves around, and point P moves to point P prime over a certain distance. That's the same distance that the wheel moves, which would be S, and the center of mass, 0, moves the same distance. So you can see that we have the center of mass, the contact point, and the segment are all equal as the wheel rolls. Now, as the wheel rolls, you can see that it's moving through an angle of theta, and we know that the segment S is equal to theta times r, the radius. We can also see that the velocity of the center of mass is equal to the distance it goes through, which is equivalent to ds over dt. And we know the angular omega is equal to d theta dt. So if we go by S equals theta r as above, and we differentiate that according to time, you get ds dt equals d theta dt times r. So basically we get the velocity of the center of mass is equal to omega times r for a rolling wheel. Another way to look at a rolling wheel is as if it had an axis that it was revolving around, going through the point of contact. And since that is not moving, since instantaneously the point P on the surface is not moving, the velocity at P is equal to 0. And we know the velocity of the center of mass is at point 0. And if you go through the derivations in the textbooks, you will see that the top of the wheel, the velocity at the top, is equal to 2 times the velocity of the center of mass. Now let's consider the kinetic energy of rolling. So we said that rolling is a combination of translation of the center of mass as well as rotation around the center of mass. So the kinetic energy of a rolling object is equal to 1/2 mv squared of the center of mass plus 1/2 inertia of the center of mass times omega squared. So this is the translational part of the kinetic energy, and this is the rotational part of the kinetic energy. So if we have a rolling wheel and it moves through an angle theta, this is its radius, and this would be part of the segment, and we have a tangential force on that wheel, and it's rolling counterclockwise, so the force is positive. we know work is equal to force times the distance, in which case this would be ds, which is equal to force tangential times r d theta. And in this case, theta would be in radians. And we know that that's equal to torque, so work becomes torque times d theta. Or we can say that dW is equal to torque times d theta. So if we integrate that from theta 1 to theta 2, and the torque is constant, so that can come out, we end up with work is equal to torque times d theta. And the units of work is joules or Newton meter radians. We also know that torque is equal to inertia times omega, angular velocity. So we can say that work is equal to the integral of I omega d omega from omega 1 to omega 2, which is equal to 1/2 I W2 squared minus 1/2 I W1 squared. And finally, power P is equal to the change in work with time. So that will be equal to torque times d theta dt, which becomes torque times omega. Now let's discuss the forces involved with rolling. If a wheel is rolling at a constant speed, there's no friction or frictional force. If a force acts on a wheel, it will either speed up or slow down. Therefore, the net force causes an acceleration of the center of mass, acceleration, center of mass, and the wheel will rotate faster or slower. This causes a change in the angular acceleration, alpha. These accelerations cause a frictional force to act at the point where the wheel touches the surface. If the wheel does not slide, the frictional force is a static force, F sub s, and A of the center of mass, acceleration center of mass, is alpha times r. So let's take a look. You have a wheel that has an acceleration of the center of mass, a linear acceleration, and here's the surface, and you have a static frictional force, and in this case the wheel is speeding up. In another case, you have the acceleration of the center of mass, but the frictional force is opposing it and the wheel is slowing down. So this wheel is slowing and this wheel is speeding up. And the frictional force determines whether the external force will speed up the wheel or slow it down. So let's look at a circular object rolling down a ramp. You can see the ramp in this diagram is at angle theta, and the wheel has a weight of mg, and it's got the normal force, and you can see the force of friction that is causing the wheel to roll. So in this case, the force of the weight times sine theta, and the force of friction, the static force of friction, is what determines the linear acceleration down the ramp. And the torque due to the force of friction is what determines the angular acceleration around the center of mass of the wheel. So let's look at this a little more closely. So linear part of this, we know that force of friction minus mg sine theta is equal to m times acceleration of the center of mass in the x direction, with positive x being up the ramp. And that's Newton's second law. The angular part of this shows that your torque is equal to I of the center of mass times angular acceleration. Well, the torque is the radius of the wheel times the force acting on it, which is the force of friction. So that's equal to I of the center of mass times alpha. But we know that negative acceleration of the center of mass is equal to alpha times r. And it's negative because it's going in the minus x direction. So if we can then solve for the force of friction is equal to minus I center of mass times a center of mass in the x direction over r squared. If we then substitute the value for the force of friction into the linear equation, number 1 here, we get, and solve for the center of mass, acceleration of the center of mass, we get acceleration of the center of mass in the x direction is equal to minus g sine theta over 1 plus inertia of the center of mass over the mass times radius squared. So with this equation, you can find the linear acceleration, a center of mass, of anybody rolling down an incline of angle theta. I'd like to go over torque again, but since torque involves the cross product of vectors, I'd first like to review that. So if you have your axes, you have vector A and B with an angle phi between them. This is y, this is x, and we have a z-axis here as well. We know that the cross product, which is A cross B, will give us a third vector that is perpendicular to the plane of A and B. So you use the right-hand rule to determine the direction of the cross product vector, and we'll call that C. You sweep your fingers from A to B through the smaller angle between them, and the thumb gives you the direction of C. So in this case, if we're sweeping from A to B, our thumb will point up. So our vector C will be perpendicular to the xz plane in the y direction. Another way of deriving the cross product, A cross B, is equal to AB times the sine of the angle between them. So this tells us that if A and B are in the same direction or in the opposite direction, then A cross B will equal to 0, because the sine of 0 and 180 degrees is 0. However, if A and B are perpendicular, then A cross B will give you the maximum value, because sine of phi will then equal 1. And we can use matrices to look at the component forms of the cross product. So A cross B is equal to, if you put that into a matrix, AX, AY, AZ, BX, BY, BZ, and that becomes AY, BZ minus BY, AZ, I minus AZ, BX minus BZ, AX, J plus AX, BY minus BX, AY, K. So this gives us our third vector perpendicular to the plane of A and B. Okay, so let's get back to torque. So in this case, we're looking at a force applied to an object or particle moving around a fixed point, not an axis. This torque causes a change in the rotational motion, and torque is equal to R cross F. So let's diagram this. You have your Y, x-axis, z-axis. You have a positional vector R, and you have a force acting on that object. And in this case, the angle is phi. And we can say that this is R perpendicular, this is R, and we also have a force perpendicular. So torque equals R cross F. So using the right-hand rule, if we put the two vectors at the origin, here's R and here's F, we would move R into F, and our torque vector would be in the Y direction. Because our thumb would point up. And we know that if the torque causes a counterclockwise motion of the object, then it's positive. If it causes a clockwise motion, then it's negative. So to rewrite this, we could say that torque is equal to Rf times sine of phi. Or it's equal to R times F perpendicular, where F perpendicular is equal to F sine of phi, or R perpendicular times F, where R perpendicular is equal to R sine of phi. And these are different ways that you can find torque. And basically, torque equals R cross F is Newton's law written for rotational motion. We're now going to discuss angular momentum, and that's given by the letter L, and that's equal to R cross P. And the units are kilograms meters squared per second, or joules seconds. And the angular momentum is the equivalent of linear momentum, only for a rotational system. And since P is equal to mv, we can say that that's equal to R cross mv, or m times R cross v, or m times RV sine phi. Different ways of finding angular momentum. And we use the right-hand rule again to find the direction of angular momentum. It is always perpendicular to the plane of R and P. So let's look at some diagrams of the right-hand rule for torque and momentum. So here you can see torque, and if we move down to momentum, same thing. The right-hand rule shows that momentum, angular momentum, points in the direction of the thumb. So we had said that angular momentum is equal to R cross P, which is equal to R perpendicular times P, which is equal to R perpendicular mv, and it's equal to R times P momentum perpendicular, which is equal to R mv perpendicular. So again, different ways of finding angular momentum. And from Newton's second law of motion for rotation, we know that torque is equal to dl dt, the change in momentum with time. That's similar to force equals dp dt in linear mechanics. If we had a system of particles, we could say that the total angular momentum of all the particles is equal to the sum from 1 to n of the momentum of all the particles in the system. And if you have a rigid body moving around a fixed axis, momentum is equal to its inertia times its angular velocity. Now let's move on to the law of conservation of angular momentum. Well, we first had conservation of energy. Then we had conservation of linear momentum. And now we have conservation of angular momentum. These are the three universal laws of conservation. Conservation of angular momentum states that if there are no external forces or torque, then angular momentum is constant. In other words, dl dt equals 0. Or final angular momentum equals initial angular momentum, or final inertia times angular velocity equals initial inertia times angular velocity. And this applies in each of the x, y, z directions. Now we're going to discuss a gyroscope and precession, which occurs due to conservation of angular momentum. So in this case, you have a spinning wheel, and as it spins, that will rotate horizontally around a fixed point. And this is called precession. And it's because the weight of the spinning wheel produces a torque that affects the angular momentum L of the spinning wheel. The angular momentum L points along the shaft and is given by L equals I times omega. And since L is parallel to R, we then know that the torque is perpendicular to L. So, and this is because torque is equal to R cross F. So let's look at the diagram. Here's R in this direction. Here's F in this direction. That gives us torque in this direction, which is perpendicular to L. But we know torque is equal to dl dt, so this torque is actually causing a change in angular momentum, a dl. But L is fixed by I times omega. In other words, the value of L can't change, so the only way L can change is by a change in direction. And this change in direction is in the same direction as torque, because dl is parallel to torque, given by that equation. So it'll precess or rotate around the z-axis. And we can find the rate of precession by looking at the precession angle versus time. So if we call omega the precession rate, that's equal to the change in the angle, d phi dt, which, if you do the calculations, comes out to mgr over I omega. And as you can see, that as omega increases, the precession angle decreases, and vice versa. So the faster the wheel is spinning, the slower the precession rate. So let's just review this one more time. the spinning wheel, and the wheel has to be spinning. If the wheel doesn't spin, then it just falls to the ground. But the spinning wheel has a weight, and that weight is mg. That produces a torque to the right. That torque changes the angular momentum based on this formula. But because the angular momentum magnitude is fixed by this formula, then the only thing that can change is this direction. And since the momentum change is parallel to the torque, it causes the wheel to precess around the fixed point. And that's why gyroscopes precess. Let's do some rotational problems. A particle moves with a position vector r equals 3ti plus 2j. Show that the angular momentum about the origin is constant. Well, we know the angular momentum is equal to r cross p. So we have r, that's equal to 3ti plus 2j, and p is equal to mv. So v is equal to dr dt, which would be 3i. Since 2j has no t in it, the derivative of that is 0. And L is equal to R cross P, which is equal to M times R cross V. And we can put those amounts in. So that's equal to M, and R is 3ti plus 2j cross V, which is 3i. Now, there's a couple ways we can do this. We can multiply 3i by those two amounts, but let me make a note of vector cross products. When you have a component that's the same, if you have I cross I, that's equal to 0. And that's because a vector AB sine phi, if phi is 0, that's 0, and if phi is 90 degrees, that's equal to 1. So I cross I is 0. However, I cross j is equal to k, because when you do a cross product, you use the right hand rule and your thumb will point in the direction of the product when you cross I into j. But note, with cross products, the order of your vectors is important. So I cross j is equal to k, but j cross I is equal to minus k. So if we come back to our problem, this is equal to m, and that would be 9ti cross I plus 6j cross I, which is equal to, well, that's 0, and j cross I is a minus 6k. So L is equal to a minus 6mk, and that's equal to a constant. Now the other way to do this is in matrix form. So you could say L is equal to M, and then you do your matrix I, J, K. And in this case, the values here would be 3t, 2, 0, and 3, 0, 0. And if you work out this matrix according to the rules, that becomes M times 0i minus 0j minus 6k, which equals minus 6mk. So either way, the answer is the same. you have a constant for your angular momentum. Let's do another problem. A solid cylinder of mass m and radius r rolls down a ramp without slipping. What is the speed of its center of mass, A, using conservation of energy, and B, using rotational kinematics? So let's diagram this problem. We have a ramp and our cylinder. The cylinder is mass m, radius r, and it's rolling down the ramp with an angular velocity of omega. Its height starts at h, and it's an angle theta. So for part A, we want to use conservation of energy to find the speed of its center of mass. So what does conservation of energy say? That potential plus kinetic energy initially is equal to potential plus kinetic energy final. So let's plug this in. The cylinder starts at the top of the ramp at rest, so kinetic energy is 0, potential energy is mgh. And at the bottom, it has a kinetic energy that's part translational and part rotational. So the translational kinetic energy is 1/2 m v squared, plus the energy is 1/2 I, and this is the center of mass, omega squared, plus the potential energy, which in this case is 0 because it's at the bottom of the ramp, so there's no height. Now for a cylinder, we know that I is equal to 1/2 mr squared, and omega is equal to v over r. So we can plug that in to our equation. So we get mgh is equal to 1/2 mv squared plus 1/2 I, which is 1/2 mr squared, times w squared, which is v over r squared, and that's v of the center of mass. So we cross out mass, and we get that gh is equal to 3/4 of v of the center of mass squared. V of the center of mass squared is equal to 4/3 gh, or v of the center of mass is equal to the square root of 4/3 gh. So that's the answer to part A. Now I want to point out something. In this case, the cylinder was rotating down the ramp without slipping. If it was sliding down the ramp and not rotating, then the kinetic energy due to the rotation would be 0, and our v of the center of mass, going through the same calculation, would be the square root of 2 gh, which is less than the rolling velocity. And the reason is, when it rolls, it's using up some of the energy rolling, which means that it has less translational kinetic energy, so the speed at the bottom will be less. Now, part B asks, using rotational kinematics, what is the speed of the center of mass at the bottom? So For part B, we're using rotational kinematics. So let's redraw our diagram again. This part's the same. In this case, we have our cylinder. This is height h. But in this case, we have our normal force. We have our weight. We have the component in the direction of the normal force, which is mg cosine theta. We have the force of the weight moving it down the ramp, which is mg sine theta. And we also have a force of friction going up the ramp. And one more thing, the distance that this travels from the top to the bottom, we'll call that d. Okay, so first we have the translational motion. And we use the kinematics for that. And that says that normal force minus mg cosine theta is equal to 0. Okay. And we'll call that equation 1. And it's 0 because the cylinder is not moving up or down into the ramp. So they balance each other out. And the other equation is mg sine theta minus friction equals ma. So these are two of our translational equations. Now we want to look at our rotational kinematic equations. And in this case, torque is equal to I of the center of mass times alpha. And the torque is caused by friction. So this friction is actually acting at the bottom of the cylinder, and it's causing the cylinder to rotate. And we know that the torque is equal to the force over the distance it's acting. And in this case, let me just draw that. You have your cylinder, you have your frictional force, and it's acting over a distance of r from the center of mass. So torque equals F times r. That's equal to I A of the center of mass. Okay, but we know for a cylinder I is equal to 1/2 mr squared, and alpha, angular acceleration, is equal to linear acceleration over r. So we're going to plug these values in. Well, first let's solve for friction. So friction is equal to I, which is 1/2 mr squared, times alpha, which is A over r, divided by r, which ends up being ma over 2, because these cancel out. Now, we're going to substitute a value for F into equation 2, and we get mg sine theta minus F, which is ma over 2, is equal to ma. Okay, these cancel out, and we get g sine theta is equal to 3/2 A, or A is equal to 2/3 g sine theta. Now, using the rotational kinematic equation of v squared is equal to v initial squared plus 2a times the distance traveled, we know that it starts at rest, so that's 0. So v squared is equal to 2a times the distance traveled, which, since we now have a up here, v squared is equal to 2 times 2/3 g sine theta times the distance traveled. Now, let's go back and look at our initial diagram. It traveled the distance d, and this is the height h, and so theta, the sine of theta, is equal to opposite over hypotenuse, or h over d. So we substitute that back in here. V squared is equal to 2 times 2/3 g times h over d, because that's what the sine theta is, times d. These cancel out. V squared is equal to 4/3 gh, or v, center of mass, is equal to square root of 4/3 gh, which is the same answer we got in part A using conservation of energy. Let's do our next problem. Two disks are spinning separately at angular speeds omega-1 and omega-2. They are then compressed together to form one disk which rotates at an angular speed omega. What is omega? What is the work done by the frictional force? So let's diagram the situation. You have two disks, and that's at omega-1, that's at omega-2, and we'll say this has moment of inertia I1 and moment of inertia I2. Okay, and we take them and compress them together so that now they're basically one disk spinning at omega. And so we want to know what that omega is. So using conservation of angular momentum, we know that angular momentum of 1, which is I1 times omega-1, plus I2 times omega-2, has to equal the sum of the two inertias times omega, or omega ends up being I1 omega-1 plus I2 omega-2 over I1 plus I2. So that would be the angular speed of the compressed disk. The second part is, what is the work done by friction? So we know work is equal to the change in kinetic energy, which is equal to K final minus K initial. And so for these disks, the final kinetic energy is equal to 1/2 I1 plus I2 omega squared, because kinetic energy is equal to 1/2 inertia times omega squared, minus the initial kinetic energy, which is 1/2 I1 omega-1 squared plus 1/2 I2 omega-2 squared. Now, we know what omega is because we just found it out up above here. So the work is equal to 1/2 I1 plus I2 times omega squared, which is I1 W1 plus I2 omega-2 over I1 plus I2 squared, minus 1/2 I1 omega-1 squared plus 1/2 I2 omega-2 squared. And if you go through the calculations, you get that the work comes out to be equal to minus 1/2 I1 I2 times omega 1 minus omega 2 squared over I1 plus I2. And that is the work done, which is related to the kinetic energy loss due to the friction of these two disks smashing together. Let's try one more problem. A disk of radius r and mass m spins about a central axis with an angular velocity omega. Suddenly, a spike is fired into a point on the disk's circumference, and the disk now rotates around this point. What is the new angular velocity? So let me diagram this to explain what's going on. We have a disk, radius r, and it's rotating through a central axis at the center of mass. We'll call that C, with angular velocity omega. And all of a sudden, a spike is fired into a point at the circumference. We'll call that point A, such that this is the new axis of rotation through point A, and it's now rotating about point A. And this is a distance r from the center of mass, which we know. And we want to know what is the new angular velocity of it going around point A. So the moment of inertia for a disk is equal to 1/2 mr squared. Okay. So that's the moment of inertia for this disk going through the center of mass. The moment of inertia going through point A is equal to, and now we're going to use the parallel axis theorem, because we know what the moment of inertia is through the center of mass, and we're a distance r from that center of mass, so we can use the parallel axis theorem. And that says that the moment of inertia is equal to I through the center of mass plus m times the distance squared from the center of mass. So in this case, I through the center of mass is 1/2 mr squared plus mr squared. So I through A is equal to 3/2 mr squared. So we want to know what the angular the angular velocity is through point A. So we use conservation of angular momentum. So that states that L1 equals L2. So L1 would be I through the center of mass times omega, and that has to equal I through A times omega prime, which we'll call the new angular velocity. So we know that I through the center of mass is 1/2 mr squared times omega is equal to 3/2 mr squared omega prime, because we found this up here. And if we cancel these out and solve for omega prime, we get omega prime is equal to 1/3 omega, which is the new angular velocity through point A.